Okay, hello everybody, and I would like to first thank the organizers for inviting me to give some of the highlights of my academic journey through NASSP. Okay, yeah, I'll just go straight to. So I first joined. I was a had a four-year BSc degree in physics from Adebe University in Ethiopia, and I was busy with my first year master's coursework when I heard the opportunity of joining NASSP, and at the time I was keenly interested in doing a cosmology project. So I was lucky enough to have people who introduced me to the program, and I applied for a NASSP honors program because I wasn't really sure about the application procedure even, and then I joined NASSP in 2008 as an honors candidate, and went through that excellent winter school program where I had the chance to interact with lecturers and students and all that. And one of those interesting interactions I had was with Professor Peter NASSP. And it was through that conversation, I think, that he realized I was probably qualified enough to be a master's student, and after the winter school, I joined the master's program in that same year. And then I joined Prof. NASSP's cosmology group, where I worked on modified gravity theories and cosmological perturbations. And most of the research discussions happened during hikes on Table Mountain. And I then carried on to do my PhD in the same group, and then moved to Northwest University, where I'm currently based, first as a postdoctoral fellow under the hostship of Professor Tebe Midupi. Just briefly to give you an idea of what my research is about, it's cosmology, and basically deals with things like the origin, large-scale structure, evolution, and ultimate fate of the universe as a whole. And in its modern scientific sense, it was based on Einstein's general theory of relativity, but later there are other attempts to reconstruct cosmology from different perspectives and so forth, where the interaction between matter and geometry is the basis for our understanding of gravity, rather than the Newtonian sense of some fictitious force field existing in the space-time. There are three ways of looking at gravity. One is the Riemannian way of looking at things, where the rotation of a vector transported along a closed curve is described by the so-called curvature thing. The other is based on a torsion notion of things. And the third approach is what we call a non-metricity-based formulation. And based on which formulation we follow, we can have a theory of gravity, the most famous being the general theory of relativity. There are some two other approaches of doing that. One is teleparallel equivalent of general relativity. The other is called the symmetric teleparallel equivalent. And from these three basic notions, you can actually expand the theory to include further generalizations. And one of the famous generalizations, and where most of my PhD and master's work was based on, is the so-called F of R gravity theory, which is an extension of general relativity. But later on, I ended up working on the generalizations of the other two notions of gravity as well, F of T, F of Q, and so forth. So this idea of gravity affecting the evolution, the dynamical evolution of the universe, has been the basis for our understanding of cosmological physics. And it was going very well until the late 1990s, when people discovered that the expansion of the universe was not behaving the way we expected to. And that was basically the discovery of this accelerated expansion of the universe. And that called for some basic understanding of what drives this acceleration, and one of the placeholder theories proposed was dark energy, and nobody knew what that dark energy is. That's why it was referred to as dark. The first attempt to explain this dark energy was to introduce this so-called cosmological constant, which happens to be the thing that Einstein introduced around 80 years earlier for something completely different. But then that was the placeholder. But there appear to be some fundamental problems, which I'm not going to go through in detail here, that does not make this cosmological constant as an attractive alternative, and there came huge zoo of alternative theories to explain this dark energy phenomenon. And some of those alternatives, which I have highlighted in purple here, are the ones that I had been mainly focusing on over the last 15 years or so of my experience in cosmology. They basically depend on either introducing some extra matter field on the right-hand side of that first equation I showed you, or introducing something on the geometry side of that Einstein field equations, and depending on which approach you follow. But of course, if you get some theories that explain the expansion of the universe, then you need to be able to constrain those models. And recently have been involved in trying to constrain these theories and come up with either a mathematically consistent set of field equations that explain the entire expansion history, or put some observational constraints from actual data. And that has been my main activity over the last few years. So as I said, the overarching theme of my research is in modified gravitation and application to cosmology. I've tried to show you some of the theories on which I have been involved in trying to understand, and the viability of these alternatives, cosmologically speaking, in terms of mathematical viability, consistency, and observational viability of these models. Just to give you what I have been doing at Northwest University since I joined there, I've been involved in teaching NASSP courses, two of which I actually managed together with support of the directors and the school and faculty structures to introduce two courses, one on general relativity and another on cosmology, which I'm currently teaching at the honors level. And then the student supervision. I've been lucky enough to have supervised or co-supervised around 16 honors students that were directly funded through NASSP, and have been also involved in the supervision or co-supervision of 10 students at the master's level, directly funded with NASSP, by NASSP. And I'm currently managing the Center for Space Research as director, which the center is the host of the NASSP node at NWU. Just to give you an idea of, and by way of advertising it as well, the Center for Space Research is one of the few centers of excellence at the Northwest University. And it has a track record of around 60 years of quality research. And there are about 25 academic staff members permanently working there, but there are about also 20 extraordinary staff from all over the world. And you can see from these statistics that they're highly rated scientists with NRF rating, good NRF ratings and so forth. It's based on the Potchefstroom and Maheken campuses, and it's one of the centers, I think, of space science and astronomy in the country. It's one of the largest, should be. It's clustered, our research is clustered into three main groups: space science, there's optical and radio astronomy, and we're trying to put a strong foothold in radio astronomy lately. And there's also a strong high energy astrophysics group there. And each one of these subgroups have their own leaders. One of the leaders is Prof. Ilani Lubser here in the audience. So we try to provide cutting edge research in space science and stellar and multi-wavelength astronomy and cosmology. And on average, in a given year, we have about 15 postdoctoral fellows and about 75 or so postgraduate students. And we're involved in national and international collaborations, including NASSP, SALT, SKA, Meerkat, and SANSA, and so forth. We're open for further collaborations and internalization efforts. And we're currently advertising for positions, so if any one of you is interested, please have a look at our website. I told you it's PR. Okay, so for me, NASSP has been really the main reason I am in my current academic trajectory, okay? And obviously, I wouldn't have been here had it not been for NASSP. So it has played a big role in my own academic trajectory and in general in transforming the country's space science and astrophysics landscape. And it has also contributed significantly to astronomy and space sciences on the rest of the continent, as you have seen from the statistics earlier. But I still think that the continent is underrepresented in this space science and astrophysics sciences globally, and programs like NASSP are the key drivers to make sure that the gap is narrowed over time and should just be further consolidated. And these are just my few wish lists for NASSP going forward. I really think that there should be some kind of competitive funding mechanism to encourage pre-honor students to join the astrophysical sciences, and there should also be a post-master's level funding at the doctoral level or postdoctoral level and so forth, to make sure that the students who finish their masters do not have anywhere else to go because of funding restrictions. And yeah, so this, I think, should be looked at, in my opinion. And strengthening the current centers, nodes, for a better student experience, while at the same time looking at expansion and increased mobility, I think, between students on different campuses to host events, arrange summer schools on rotating node basis, for example. That would be a nice thing to make sure that there's a close connection between the different nodes that at the moment seem to be working more independently than as one family of NASSP. And the funding for inviting local international experts as visiting lecturers, for example, for a few weeks. I had the privilege of having many leading experts in the field coming to give lectures for a few weeks, and that was a very nice experience, in my opinion, so that should, I think, be encouraged. And creating closer partnerships with other NASSP-like programs on the continent, and increasing Pan-African participation as well would be a great thing going forward, I think. And finally, I would like to just say that I'm very grateful for NASSP. Thanks.
Thank you very much.